Now for this problem, we are going to do another ICE table. It says the following reaction has an equilibrium constant Kc, so our equilibrium constant value is given at 0.083. It says if you have 0.74 moles of COCl2 in a 1 liter container initially, how many moles, not molarity, of COCl2 will be present when the system reaches equilibrium? This is an ICE table problem. I'm going to write my ICE table down here this time. And write out my reaction. And when I have a Kc value, I like to write it out at the end there. You don't have to do that. That's just something that helps me stay organized. Now I have my molarity. I have my I, C, and E rows. And it says I have 0.74 moles in 1 liter. So that's just 0.74 molarity. And the question is, how many moles of COCl2 will be present when the system reaches equilibrium? So the number that we need is this one right here, and we don't have it yet. We also know that there's no products at equilibrium. It doesn't specifically mention that, but again, if it doesn't mention it, fill in zeros there. Every once in a while, you'll see a problem that has values here, and it'll say initially, or if you have products initially, but we haven't run into that yet. So this is the information we have from the problem statement and the setup. Now we have to figure out how to solve this. To solve this, we know that the reaction, because there are no products, must convert reactants into products to get to equilibrium. Imagine that QC equals 0 for this, just to touch base with QC versus KC. But in order to do this, we have to take minus X, and X is because we don't know how much reaction is going to occur. And then, but some of the reactants will be taken away, an unknown amount, and it will be converted into products. And when it does, it will be converted into each of our products. That's what this plus X means here for each of these. Now we're looking for the number here. We don't know the number yet, but we do know that the equilibrium concentration of COCl2 will be this expression. And we know that our products, 0 plus X, will just be X. And this is an ICE table problem with X's. And again, these are going to be 90% of our ICE table problems. And I better have a little more coffee if I'm going to solve this one. Okay, we know our Kc value. We know our Kc expression. Sorry, I got my Kc value from up here or here. We know our Kc expression. It's concentrations of products raised to coefficients over concentrations of reactants. And we know at equilibrium that our concentration of each of our products is X. And we know at equilibrium our concentration of our reactant is 0.74 minus X. So now we have one unknown, one variable, X, and it's in an equation form. So let me write that out. (0.083) equals X squared over 0.74 minus X. With one equation and one unknown, now it's off to the Algebra Olympics. So I'm going to cross multiply to get my X squared on one side and multiply my 0.083 times 0.74 minus X. I get 0.083 times 0.74 equals 0.0614 minus 0.083x. Yes, we need to solve this using the quadratic equation. To solve this, we need to get it into everything on one side so that it's equal to 0. X squared, minus, well, plus, when I take this over to the other side, 0.083x minus 0.0614 equals 0. If you don't remember your quadratic equation, it looks like this. X equals minus b plus or minus b squared minus 4ac over 2a, where a is the number that goes with the x squared term, b is the number that goes with the x term, and c is the number that is just a number. And that includes the minus sign or the plus sign for each of these. So to fill this in now, it's going to be minus 0.083 plus or minus, and I may have to go into overtime here. Let's see, there we go. So b squared, 0.083 squared minus 4. A is 1. And C is minus 0.0614. And that's all over 2 times A. A is just 1, so just all over 2. Now the way I noticed do this is I turn my pluses, my 2 minuses into pluses, and now I'm going to do this term underneath here. So, and by the way, mathematically, if I'm taking this number, which is my b, squaring it, adding something to it, and then taking the square root, the answer for this part has to be bigger than 0.083. 0.083 squared plus 4 times 1 times 0.0614. So did I hit plus already? Yep. So 4 times 0.0614. I get that number. Yep. And then I hit the square root and I get 0.5. So this is going to be taking this first term, 0 minus 0.083 plus or minus 0.502 over 2. My two roots for this are going to be, one of them is going to be positive and one of them is going to be negative. The negative answer, taking the negative root here, so x is an amount of reaction. So if x is negative, that means that this answer will be negative, which is physically impossible. You can write it down, but it's not going to be the one we need. Let's see. So 0.502 positive minus 0.083. I get 0.419. 0.502 negative minus 0.083. Negative 0.585. So this root does not make physical sense, so it will not be correct. This answer here, 0.419, that is what my x value has to be. And sometimes what I do is I put another E line here and actually fill in the numbers for my equilibrium molarities. These are going to be 0.419. My concentration of my COCl2 will be 0.74 minus 0.419. And since that's what the problem asks for, 0.74 minus 0.419. I get 0.32, which is not one of the answers, which means I have to go back and check my work. Let's try this again.
I think it's in the quadratic equation.
I think you're right, yes. 0.06, 4 times 0.06, 0.25. Oh, did I forget to square root it? I bet you that's what I did. No? Well, anyway, let's do it again. Thank you, Seldon. 0.083 squared plus 4 times 0.0614, then square root it. Huh. Oh, that's it. I forgot to divide it by 2, I bet. Minus 0.083 divided by 2. There we go. 0.20, well, 0.210. Thank you for your help. And now let's see what I get. 0.74 minus 0.21, 0.53. All right, way up here. 0.53. Thank goodness for multiple choice problems that have an answer. So let's see if I can back out, show it to you all at once. Any questions about that one? Because this is representative of problems that you will do upcoming as well.